Saturn is less dense than water. Drop it in an ocean large enough to hold it, and it floats. That single fact sounds like a trick question on a science test, but it is the starting point for everything strange about this planet, because the same object that would bob on the surface of a giant bathtub has a core running hotter than the surface of the sun. It generates winds that move at 1,800 kilometers per hour. It hosts a storm locked into a perfect geometric shape that has held for as long as we have been watching. These two things should not exist in the same object. They do. Here is what makes Saturn genuinely disorienting. From a telescope, it looks peaceful. The rings catch light in a way that seems almost architectural. The pale yellows and tans of the cloud bands look soft, almost watercolor. People have pointed telescopes at Saturn for 4 centuries and described it as the most beautiful object in the sky. That image is the most misleading thing in the solar system. The beauty is the outer layer of an atmosphere powered from within by temperatures that exceed 10,000 Kelvin. Everything calm-looking on the surface is sitting on top of something that has been burning since before Earth existed. Saturn is the 6th planet from the Sun, the 2nd largest in the solar system, and by almost any measure the strangest. Its diameter is 9 times Earth's. Its mass is 95 times Earth's. Yet its average density is 0.69 grams per cubic centimeter, lower than water, lower than any other planet. This is not a minor quirk. It tells you exactly what Saturn is. There is no solid surface, no ground, no place where the atmosphere ends and something firm begins. Just gas that thickens and heats as you descend, with no bottom in any meaningful sense. The calmness you see from a telescope is the top of an abyss. If you find comfort in these gentle explorations of space and science, I'd be grateful if you'd consider subscribing and giving this video a like. I'd love to know where you're watching from and what time it is for you. Feel free to drop your location and time in the comments below. What lies beneath that pale haze is what this is about. Saturn's atmosphere contains winds that move 6 times faster than the strongest hurricane ever measured on Earth. Not gusts, sustained jet streams, permanent, global, and still accelerating in some regions. The energy driving those winds does not come from the Sun. Saturn is nearly 10 times further from the Sun than Earth is, and it receives roughly 1% of the solar energy Earth does. The power behind those winds comes from inside the planet itself, from a heat source that has been radiating outward for 4.5 billion years and has not come close to running out. At Saturn's north pole, there is a storm in the shape of a hexagon. Each side of that hexagon is longer than Earth's diameter. At the center is a rotating vortex with an eye 50 times larger than a typical hurricane on Earth. This storm has maintained its precise 6-sided geometry for every second of every year that we have been capable of detecting it. No other planet in the solar system has anything like it. Scientists have a partial explanation. The full picture is still open. Once every 30 Earth years, Saturn produces a storm that grows until it encircles the entire planet. The lightning generated during these events fires more than 10 times per second at peak intensity. Individual lightning bolts on Saturn release up to 8 billion joules each. Earth's most powerful lightning discharges a fraction of that. The 2010 storm, one of these planetary-scale events, released energy during its peak comparable to a significant fraction of everything Saturn radiates to space. One storm, channeling the output of an entire planet. The rings, which look permanent and solid from Earth, are actively falling into Saturn's atmosphere right now, roughly a ton of material every second. They will be completely gone within 100 million years. The most recognizable structure in the solar system is temporary. It is also the debris field of a moon Saturn tore apart with its own gravity. And then there is Enceladus, a moon small enough to fit inside a single US state, sitting inside Saturn's radiation belts, actively spraying water from a confirmed global ocean into space through geysers at its south pole. Those plumes contain organic molecules, sodium salts, and molecular hydrogen. Hydrothermal chemistry, the signature of the same conditions that sustain life in the deepest parts of Earth's oceans. This is one planet, one system. Before we are finished, you will have seen the interior structure, the impossible geometry, the planetary-scale electrical storms, the dying rings, the alien moons, and the open questions that 4 centuries of observation and a spacecraft that spent 13 years in orbit have still not resolved. Jupiter is larger. Jupiter gets more attention. By the time we are done here, you will not look at it the same way again. To understand what makes Saturn genuinely disturbing, you have to start with what it actually is. Not the postcard image with the rings, but the physical object itself. Saturn's diameter is roughly 9 times the diameter of Earth. That number sounds manageable until you sit with it. 9 Earths lined up side by side would stretch from one edge of Saturn to the other. Its volume is large enough to fit approximately 760 Earths inside it. Not stacked neatly, not with any particular arrangement, just 760 of our entire planet packed in. You could take every continent, every ocean, every mountain range on Earth and replicate it 760 times and still not fill Saturn. The mass is 95 times Earth's. These numbers are almost too large to be useful. They start to blur after a while, the way very large sums of money eventually stop feeling real. So here is a comparison that might land harder. If you took Saturn out of its orbit and placed it at the center of our solar system where the Sun currently sits, it would not reach Earth. Saturn is not the Sun. It doesn't come close in size. But it would extend outward to roughly where Venus orbits now, about 108 million kilometers from its center. Everything inside that radius, Mercury, Venus, the Sun's former position, would be submerged inside the planet. 2 entire worlds would sit within the body of Saturn itself, and we haven't even started talking about the rings yet. The rings deserve their own moment here. They span roughly 270,000 kilometers from their inner edge to their outer edge. That distance is about 2/3 of the gap between Earth and the Moon. If you positioned the rings around Earth, they would extend nearly to the Moon before they stopped. And yet, for all that width, they are only about 10 meters thick on average. The ratio of width to thickness makes a sheet of paper look chunky by comparison. From the side, the rings effectively vanish. Edge on, this structure that spans hundreds of thousands of kilometers collapses into a line too thin to perceive. Everything about Saturn operates at proportions that make normal comparisons feel inadequate. Here is where it gets strange. Despite a mass 95 times greater than Earth's, Saturn has an average density of about 0.69 grams per cubic centimeter. Water has a density of 1.0. Saturn is less dense than water. If you could somehow build a bathtub large enough to hold it, and fill that bathtub with water, Saturn would float. That is not a thought experiment designed to be cute. It is telling you something fundamental about what this planet actually is. Saturn is not a denser, larger version of Earth. It is not rocky ground scaled up to incomprehensible size. It is overwhelmingly gas. Hydrogen and helium account for almost all of it. The bulk of Saturn's volume is material so diffuse, so loosely held together by gravity, that liquid water is denser than the average of the entire planet. This matters because it changes what Saturn is. Earth has a surface. You can stand on it. Mars has a surface. Titan, Saturn's largest moon, has a surface. Saturn does not. There is no level at which a falling object would land. No altitude where the ground begins. No boundary between atmosphere and planet. You descend into Saturn the way you descend into an ocean, gradually encountering more resistance, more pressure, more heat. Except the ocean never has a floor. At the cloud tops, the pressure is roughly Earth's atmospheric pressure at sea level. Reasonable, survivable in terms of pressure alone. Drop further, and the pressure doubles, then triples, then keeps climbing. The temperature climbs with it. The hydrogen gets denser. What began as something that resembled gas starts behaving more like a liquid, but there is no sharp transition, no moment where the atmosphere officially ends and the planet officially begins. They are the same thing. Probe designers have encountered this problem directly. The Galileo probe, built for Jupiter rather than Saturn, but facing the same fundamental challenge, had a heat shield and a parachute, and instruments hardened against extreme conditions. It survived for about 57 minutes after entering Jupiter's atmosphere before the pressure and heat destroyed it. It never reached a surface. It was simply crushed by an atmosphere that got too heavy. Saturn would do the same thing to anything we sent into it. The crushing is not dramatic or sudden. It is just relentless, the weight of a planetary column of gas pushing down from above, growing heavier every kilometer you fall. The mass that produces that pressure is mostly hydrogen. Simple, lightweight hydrogen, the most abundant element in the universe. Saturn is not exotic in composition, it is exotic in quantity. Enough hydrogen piled up in one place, under its own gravity, becomes something that behaves nothing like the gas you know. It becomes thick, layered, stratified into zones of different density and temperature that stack from the visible cloud tops down to pressures we have never created in a laboratory for more than a fraction of a second. The interior of Saturn is not a mystery because it is made of unusual things. It is a mystery because the conditions down there are conditions that nothing we have built can withstand long enough to observe. What you are looking at when you see Saturn in a telescope is the very top of an atmosphere 270,000 kilometers wide, where ammonia crystals have frozen out of the gas and formed a pale yellowish haze. That haze is the surface as far as telescopes are concerned. Everything below it is inference. Everything below it is math and physics applied to conditions we can barely replicate. There is no ground, no surface, no place to stand, just an atmosphere that thickens and heats as you fall, with no bottom in any meaningful sense. The stripes you see on Saturn in photographs are not markings on a surface. There is no surface. What you are looking at when you see those pale bands and darker belts is something stranger. Organized weather at planetary scale, running in opposing directions at different latitudes, locked into position by forces that have almost nothing to do with the sun. On Earth, weather is solar. The sun heats the equator more than the poles. Warm air rises, cold air sinks, and pressure differences push air around the planet. Every storm, every wind pattern, every cloud system traces back to that basic inequality in heating. Saturn does not work this way. Saturn is nearly 10 times further from the Sun than Earth. At that distance, the sunlight arriving at Saturn is roughly 1% as intense as what falls on Earth. 1%. That is not enough to drive a calm afternoon breeze on a temperate planet, let alone the atmospheric machinery visible from a backyard telescope. Yet the atmosphere moves. It is furiously, continuously, permanently active. The energy has to come from somewhere else. That somewhere else is the planet itself. Saturn generates heat internally, left over from its formation 4.5 billion years ago, and it radiates more energy outward than it receives from the Sun. That internal heat rises through the atmosphere the same way heat rises from a stovetop burner, not evenly, but in organized columns and sheets. Where it rises, you get the lighter zones. Where cooler gas sinks back down, you get the darker belts. These are not decorative bands. They are the visible surface of a circulation system built from the inside out. The rotation makes it precise. Saturn spins fast. A full rotation in just over 10.5 hours, which is extraordinary for an object 760 times the volume of Earth. That spin organizes the rising and sinking columns of gas into tight east-west bands through the Coriolis effect. The result is a set of permanent jet streams running in alternating directions at different latitudes, each one moving at speeds that would be unrecognizable to anyone who has only ever experienced Earth's atmosphere. These jet streams do not drift or shift the way Earth's do. They stay locked. Now look at what those jet streams are actually made of. The atmosphere is mostly hydrogen, about 96% hydrogen, 3% helium, and then trace amounts of methane, ammonia, and water vapor that together make up less than 1% of the total. Hydrogen and helium are both colorless, which is why Saturn's atmosphere, at first glance, should look like nothing much at all. The color comes from that small fraction of other molecules. Ammonia is the most important one at the level we can see, high in the atmosphere where temperatures drop to around 80 Kelvin, roughly negative 190 degrees Celsius. Ammonia gas freezes into crystals and forms clouds. Those ammonia ice clouds are what we actually see when we look at Saturn. The pale yellowish-white color of the planet comes from sunlight scattering off frozen ammonia. That is the top of the atmosphere. That is all we can directly observe. Below the ammonia cloud layer, the pressure and temperature climb. The next major cloud deck is made of ammonium hydrosulfide, a compound that forms when ammonia and hydrogen sulfide react at higher pressures and temperatures. This layer sits somewhere around 3 to 5 bars of pressure, several times the atmospheric pressure at Earth's sea level. Nobody has seen it directly. Below that layer there is thought to be a water cloud deck, where temperatures are high enough for water to exist in liquid or ice form, at pressures somewhere around 10 to 20 bars. Still deeper, the pressure keeps rising, the temperature keeps climbing, and the chemistry becomes increasingly difficult to model. Here is the problem. The deepest probe ever sent into a gas giant was the Galileo atmospheric probe, which entered Jupiter in 1995 and transmitted data down to about 22 bars of pressure before it was destroyed by the conditions. 22 bars is not deep. In terms of the total interior of a gas giant, it is essentially the skin. We have never sent anything into Saturn's atmosphere at all, not a single dedicated atmospheric entry probe. Everything below the ammonia cloud tops is inferred. The composition, the cloud structure, the pressure-temperature profile, these are calculated from physics and from what we can observe remotely with spectrographs and telescopes, not from instruments that have ever been there. What makes this stranger is that the part we can see is the least interesting part. The ammonia haze is almost featureless compared to what must be happening in the layers beneath it. The storms that occasionally break through to the visible level are driven by convective forces in the water cloud region thousands of kilometers deeper, which means the atmosphere we can photograph is just the ceiling of a system we have never accessed. The pale yellow bands, the organized jet streams, the smooth zones and darker belts, these are the top of something vast, layered, and almost entirely unexamined. Everything we know about what lies beneath that pale yellow haze comes from physics and mathematics, not from any instrument we have ever managed to send down into it. The fastest wind speed ever recorded during a hurricane on Earth was a little over 300 kilometers per hour, and that storm killed people and destroyed buildings across hundreds of miles. It was considered catastrophic. Insurance companies used words like unprecedented. Meteorologists tracked it around the clock. That number, 300 kilometers per hour, represents roughly the outer limit of what Earth's atmosphere can sustain in a rotating storm system. Saturn's equatorial winds move at around 1,800 kilometers per hour. Not during a storm, not during some rare extreme event, all the time, permanently, as a baseline condition that has been measured every time we have pointed an instrument at the planet. That is not a small difference. 6 times faster than the worst hurricane in recorded human history, sustained indefinitely, wrapped around a planet 9 times wider than Earth. To get a sense of what that actually means, consider that the speed of sound in air at sea level is about 1,200 kilometers per hour. Saturn's equatorial winds are moving faster than sound. They are supersonic, not at the edge of some exotic deep layer we cannot access. At the cloud tops, the part of Saturn we can actually observe directly, the part that looks calm and banded and almost serene in photographs. These are not gusts. That distinction matters. A gust is brief, local, a temporary spike in velocity caused by some passing disturbance. What Saturn has are organized jet streams, atmospheric rivers moving in fixed latitudinal bands, each one flowing in a specific direction at a specific speed, some eastward, some westward, stacked next to each other across the planet like lanes of a highway where every lane is moving at a different velocity and none of them have ever been known to slow down. Voyager 1 measured them in 1980. Voyager 2 measured them in 1981. Cassini measured them continuously for 13 years. The velocities are consistent. The jet streams persist across decades of observation without any sign of weakening or changing structure. Whatever is driving them has not varied meaningfully. Only in the 40-plus years we have had instruments capable of detecting them. Here is the problem. On Earth, wind comes from the sun. Solar radiation heats the equator more than the poles. It heats land differently from ocean. Those temperature differences create pressure gradients, and pressure gradients move air. The sun is the engine. This model works well for Earth, reasonably well for Venus, passably for Mars. It does not work for Saturn. Saturn orbits the sun at about 1.4 billion kilometers, nearly 10 times the Earth-Sun distance. At that range, the solar energy hitting Saturn's cloud tops is roughly 1% as intense as what hits Earth. The sun is barely a bright star from Saturn's perspective. It cannot be heating the atmosphere unevenly enough to drive 1,800 km/h jet streams. The math does not come close to working. So where is the energy coming from? Saturn itself. The planet radiates approximately 2.3 times more heat outward than it receives from the sun. There is an internal energy source operating inside Saturn that is powerful enough to pump more heat into the atmosphere than the nearest star can deliver from the outside. That internal heat drives convection, hot material rising, cool material sinking, and the planet's rapid rotation organizes those convective flows into the tight, persistent east-west jet streams visible at the cloud tops. The rotation is fast. Saturn completes a full day in about 10.5 hours. That spin, combined with the internal heat, generates and locks those jet streams into their positions. The Coriolis forces on a planet rotating that quickly are enormous, and they turn rising columns of hot gas into horizontal rivers rather than vertical plumes. Now think about what 1,800 km/h actually feels like as a physical force. At that speed, the dynamic pressure on any surface facing into the wind is not something human engineering has ever been designed to withstand at planetary scale. Imagine standing at the nose of a supersonic aircraft in open air, no cockpit, no windscreen, just you and the airflow, and then imagine that condition extending in every direction for thousands of kilometers with no terrain to break it, no ground to anchor against, and no way to get out of it because there is no outside. There is no solid surface anywhere beneath you. The wind is not blowing across a landscape. It is the environment. It goes all the way down to wherever the atmosphere transitions into something denser, and that boundary is not a flaw. It is just a place where the wind encounters more resistance and has to do more work. Any structure placed in Saturn's equatorial atmosphere at cloud top level would not bend or flex. It would come apart. Not slowly, not over hours. The forces involved would disassemble anything built from materials we currently know how to produce, at the speeds we currently know how to achieve. before it had time to transmit a signal back to Earth telling us it was in trouble. The Galileo probe that entered Jupiter's atmosphere in 1995, a much slower atmosphere than Saturn's, was destroyed in less than an hour. Saturn would be faster and more complete about it. What makes this stranger still is that the jet streams are not chaotic. They are organized. Each latitude band flows in a specific direction, and the alternating pattern, eastward, westward, eastward, is coherent across the entire planet. Saturn's winds are violent at a scale beyond anything on Earth, and yet they run with the regularity of something mechanical. Clean, directional, persistent. The chaos is in the speed. The structure is almost disciplined. That combination, extreme force operating through highly organized patterns, is part of what makes Saturn's atmosphere so difficult to model accurately even now, after decades of direct measurement. The winds that drive all of this are not borrowed from sunlight. They are powered by something stranger and deeper, something that has been burning inside Saturn since before Earth existed. At Saturn's North Pole, there is a storm in the shape of a perfect hexagon, not roughly hexagonal, not a rounded blob that sort of suggests 6 sides if you squint at it the right way. A precise, clean, 6-sided geometric figure sitting at the top of a gas giant, with walls of roaring wind holding that shape decade after decade. Voyager 1 spotted it in 1981. Voyager 2 flew past and confirmed it. Cassini arrived at Saturn in 2004 and spent 13 years photographing it in detail. The hexagon was there every single time. No other planet in the solar system has anything like this. Not Jupiter, not Neptune, not any of the thousands of exoplanets we have catalogued from a distance. This feature is unique, and that alone should give you pause. The scale is the first thing to absorb. The hexagon spans roughly 30,000 kilometers across, which means each of its 6 sides is longer than the entire diameter of Earth. The walls of the storm are jet stream winds moving at around 320 kilometers per hour, almost exactly 200 miles per hour. That is not the wind inside the storm. That is the boundary of the storm, the geometric edge that holds the shape, running continuously around all 6 sides. At the center sits a vortex, a rotating hurricane-like system with an eye approximately 2,000 kilometers across. A typical hurricane on Earth has an eye somewhere between 30 and 65 kilometers wide. Saturn's central vortex eye is roughly 50 times larger than that. The hurricane at the center of a feature this enormous is itself a structure that would swallow a continent. The fluid dynamics explanation for how this happens is real, and it has been partially reproduced in laboratory experiments. When a fast jet stream flows around a slower rotating body of fluid, under the right conditions of speed, viscosity, and rotation rate, the jet stream does not stay circular. It develops instabilities. Those instabilities can lock into geometric patterns, producing triangles, squares, pentagons, hexagons, depending on the specific combination of parameters. In controlled tank experiments where scientists spin a central cylinder inside an outer ring of fluid at different speeds, hexagonal patterns appear. So the basic mechanism is not mysterious. Differential rotation under specific conditions can produce corners instead of curves. What is extraordinary is the precision required. The conditions that produce a hexagon rather than a circle or a pentagon, or just chaotic turbulence, occupy a narrow range. The ratio of the jet stream speed to the rotation speed of the underlying atmosphere has to fall within specific bounds. The depth of the jet has to be right. The temperature gradient has to cooperate. On Earth, even when similar instabilities develop in polar vortices, they are loose and shifting. They wobble, they break down, they reform in different configurations. They do not lock into a clean 6-sided shape and then hold it for 40 years without drifting. without breaking, without losing its geometry. Saturn's hexagon does not wobble. It sits there. It is architectural. Cassini gave scientists something Voyager could not, which was time. 13 years of close observation meant researchers could watch the hexagon through an actual Saturnian seasonal cycle. Saturn's year is about 29.5 Earth years long, so Cassini caught roughly half of a full seasonal cycle. What it documented was striking. When Cassini arrived, the North Pole was in winter. The hexagon at that time appeared blue, a deep blue that stood out sharply from the pale yellowish banding of the lower latitudes. As the years passed and Saturn moved through its orbit, northern spring arrived, then northern summer began approaching. Sunlight started reaching the pole more directly, and the hexagon changed colour. It shifted from blue to gold over the course of roughly a decade, a slow transformation driven by photochemistry. More sunlight reaching the polar atmosphere meant more ultraviolet radiation breaking down methane and other organic molecules, creating complex haze compounds that settled as a golden brown layer across the region. The colour change was seasonal. The shape did not change at all. The depth of the hexagon is one of the most unsettling aspects of the whole feature. Early analysis suggested it extended at least a few hundred kilometers down into Saturn's atmosphere, well below the visible cloud tops. More recent modelling work suggests it may reach thousands of kilometers deep, down into pressure and temperature regimes that no probe has ever approached. If that is accurate, the hexagon is not a surface phenomenon. It is a deep structure, something woven into the atmospheric dynamics at multiple layers simultaneously, with the boundary jet stream maintaining its geometric shape from the top of the visible clouds down into regions where the pressure is crushing and the temperature is climbing toward conditions we can barely reproduce in a laboratory. The stability of the shape across that depth range is something fluid dynamicists are still working to fully explain. One natural question is whether Saturn's south pole has anything similar. The answer is complicated. Cassini observed a powerful rotating vortex at the south pole, a hurricane-like storm with a clear eye wall and organized structure. It is enormous and striking, but it is circular, not hexagonal. The South Pole does not have a hexagon. Nobody fully understands why the geometry is different at each pole. The two poles should be operating under broadly similar physical constraints, both influenced by Saturn's rotation, both sitting at the same distance from Saturn's axis. Yet the north produces a hexagon and the south produces a cyclone. Whether this difference is fundamental to Saturn's interior structure, or whether it reflects the asymmetry of the seasonal cycle at the time we were observed, or something else entirely, is an open question. The most common mistake when looking at the hexagonal storm is to treat the fluid dynamics explanation as a complete answer. Yes, rotating fluid systems can produce geometric jet stream patterns under the right conditions. The laboratory experiments confirm the basic physics, but those same experiments also show how fragile and transient these patterns are. They form and break down over the course of minutes in a tank, producing conditions that maintain the pattern for decades, at the scale of a planetary atmosphere, through seasonal changes, through the continuous injection of energy from Saturn's internal heat below and solar forcing above, without the shape ever losing its precision, is not something the basic experiment explains. It identifies a mechanism. It does not explain the persistence. After decades of staring at it, the most honest answer scientists have is that they understand the mechanism that could produce it, but not why Saturn has maintained it with such precise, almost architectural stability for as long as we have been watching. Once every Saturnian year, roughly every 30 years of Earth time, Saturn has a catastrophic storm. Not a local disturbance, not a regional weather event, A storm that starts as a white smear in the cloud tops and grows until it wraps entirely around the planet. Every person alive during one of these events who thought to look at Saturn through a telescope saw something different from what had been there the month before. The planet itself had changed. That is the scale we are talking about. These storms have a name. Astronomers call them Great White Spots, and they have been showing up in the record books at roughly 30-year intervals for as long as we have had telescopes capable of seeing them. 1876, 1903, 1933, 1960, 1990. Each entry in that list represents a moment when Saturn's atmosphere did something violent enough to be visible from 100 million miles away, without any specialized equipment, without any spacecraft. Just a lens and a patient observer, and a planet suddenly doing something it had not been doing the week before. The timing is not random. These storms tend to emerge during Saturn's northern hemisphere summer solstice, when that part of the planet is receiving the maximum solar heating it ever gets. That sounds like an explanation. Seasonal warming triggers atmospheric instability, storm forms, storm grows. It is the kind of logic that works on Earth. But there is a problem with that explanation, and it is a significant one. The amount of solar energy Saturn receives at its northern hemisphere summer solstice is not close to sufficient to drive storms of this magnitude. Saturn is nearly 10 times further from the Sun than Earth. The solar heating difference between Saturn's summer and winter is real, but it is small. It cannot be the fuel source for what these storms actually release. The fuel is internal. Saturn's interior has been storing heat since the planet formed 4.5 billion years ago, and that heat has to go somewhere. Most of the time, it bleeds outwards slowly, driving the wind speeds and the banding and the general atmospheric violence that runs continuously. But the great white spots appear to represent something different. They are moments when the slow bleed is not enough, when the stored energy finds a pathway to the surface and erupts. The seasonal signal from the Sunday may be the trigger, the small perturbation that destabilizes a system that has been building pressure beneath the surface for decades. But the energy behind the eruption is not solar. It is gravitational and thermal, accumulated over the full 30-year cycle between events. Think of it as a pressure cooker. Saturn's interior traps enormous amounts of convective energy. The atmosphere above it acts as a partial lid. For roughly 30 years, the lid holds. Then something changes. A threshold is crossed, and the energy finds a way out. A white spot appears. Within days, it is thousands of kilometers across. Within weeks, it is the size of a continent. Within months, the storm head and the tail it drags across the planet have circled Saturn completely, turning one latitude band into a continuous belt of churning white cloud. The 1933 event is particularly well documented for its era, and it tells you something about the scale. That storm grew rapidly enough that amateur astronomers across Europe and North America were tracking it within days of its appearance. By the time professional observatories turned their full attention to it, the storm had already grown to a size that made comparisons to anything on Earth feel inadequate. Countries were used as units of measurement. The storm was larger than several countries combined. The 1990 event was caught by the Hubble Space Telescope shortly after its launch, providing the best imagery scientists had ever obtained of one of these phenomena. Hubble watched the 1990 storm expand in real time, and even with that documentation, the theoretical picture of what was actually happening inside Saturn remained incomplete. The energy numbers are not comfortable. During a fully developed Great White Spot event, the power being released into Saturn's atmosphere represents a significant fraction of the total energy Saturn radiates to space at any given time. Saturn already radiates more energy than it receives from the Sun, roughly 2.3 times more, which means it has an enormous baseline energy output. These storms are releasing a substantial portion of that on top of everything else. a single atmospheric eruption channeling energy that rivals what an entire planet puts out continuously. There is no storm on Earth that exists in the same conversation. There is no frame of reference in terrestrial meteorology that gets you anywhere close. What the storms leave behind is also worth noting. After the storm head circles the planet and the most violent phase passes, the affected latitude band is chemically altered. Cassini documented this directly with the 1990 storm's aftermath, and in more detail during later events. The storm does not just displace air, it drags material up from deeper layers, mixing atmospheric chemistry in ways that take years to settle back toward equilibrium. Saturn, after a great white spot, is not quite the same Saturn as before. The upper atmosphere carries the chemical signature of what just happened, and that signature persists. For most of the 20th century, scientists believed the 30-year cycle was reliable enough to plan around. The pattern had held through 5 observed events without a significant deviation. The mechanism was not fully understood, but the timing seemed predictable. Then 2010 arrived. A great white spot erupted in Saturn's northern hemisphere at an unexpected latitude and at a point in the Saturnian calendar that did not match the established pattern. Scientists had not been anticipating it. The models had not flagged it. Amateur astronomers noticed it before anyone with a professional prediction on the table could have warned them to look. The 2010 storm arrived early, breaking the pattern that had held for over a century of observations, which suggested that whatever was driving these events from deep inside the planet was not running on a clock anyone fully understood. On December 5, 2010, amateur astronomers around the world noticed something forming on Saturn that had not been there the week before. It was small at first, a bright white patch in the northern hemisphere, sitting against the pale-banded clouds like a smudge that did not belong. Professional observatories confirmed it within hours. Cassini, which had been orbiting Saturn since 2004, swung its instruments toward the northern latitudes and started recording. What followed over the next several months was one of the most violent atmospheric events ever documented in the outer solar system, unfolding in real time, in extraordinary detail, with humanity watching from a spacecraft close enough to count the lightning strikes. Within 3 weeks of that first sighting, the storm had expanded to roughly 10,000 kilometers north to south. That is about the distance from the equator to the North Pole on Earth. The storm covered that span in 21 days. By the time the main body reached full development, it stretched approximately 17,000 kilometers from east to west. Then there was the tail. The storm produced a trailing streamer of disturbed atmosphere that extended roughly 100,000 kilometers behind it, nearly 1/3 of the way around the entire planet. If you could somehow stand on Saturn and look in any direction, there was a meaningful chance you were looking at this storm. From space, the images were extraordinary. The white convective plume erupted upward from deep inside Saturn's atmosphere and spread laterally as it hit the upper atmospheric layers. A bright churning mass visible even through modest ground-based telescopes. Cassini's cameras caught the structure in detail that ground-based imaging never could. Towering convective towers dragging up material from hundreds of kilometers below the visible cloud tops, spreading outward into a shield of bright cloud that grew wider every day. The color contrast was stark. Saturn's atmosphere is normally pale and subdued, its banding soft and gradual. This storm was white and violent against it, wrong-looking, the way a bone looks wrong when it is at the wrong angle. The disturbances did not stay local. One of the more remarkable findings from Cassini's data was that the storm's influence reached Saturn's equator, tens of thousands of kilometers away from the storm's origin, latitude of roughly 37 degrees north. Pressure waves and temperature anomalies propagated outward through the atmosphere and began disrupting the equatorial jet stream. That had been running steadily for as long as we had been measuring it. A storm that started in one hemisphere was rewriting the atmospheric dynamics of the entire planet. Then there was the lightning. At peak intensity, the storm was generating more than 10 lightning flashes per second. Not 10 flashes over the course of a storm. 10 flashes every second, sustained, for weeks. Each individual bolt was releasing energy that dwarfs anything Earth's atmosphere produces. The radio noise from this electrical activity was so intense that Cassini's instruments were detecting Saturn electrostatic discharges, the radio wave signature of lightning, almost continuously during the storm's peak. The scale of electrical activity happening inside this system had no terrestrial comparison worth reaching for. Earth's most violent thunderstorms generate perhaps a few flashes per minute at their most intense. Saturn's 2010 storm was running at rates that made even that seem trivial. Consider the energy budget. Saturn radiates roughly 2.3 times more energy into space than it receives from the Sun. That total radiated energy, across the entire surface of a planet, 95 times the mass of Earth, is an enormous number. The 2010 storm released energy during its peak that represented a significant fraction of that total. A single storm on a single planet was briefly channeling power comparable to a meaningful portion of everything Saturn emits to the universe. This was not a weather event. It was an energetic release on a planetary scale, a valve opening in a pressure system that had been building for decades. That last part matters. Saturn does not produce these storms randomly or frequently. The great white spots come roughly every 30 Earth years, tied to the northern summer solstice. This was because it takes that long for Saturn's interior to accumulate enough thermal instability to break through. The atmosphere acts as a lid. Below it, heat builds, rising convective cells push upward and are suppressed, pushed back down, forced to wait. And then, at some threshold nobody has precisely identified, the lid fails. The suppressed energy punches through, and the storm erupts upward faster than the atmospheric circulation can contain it. What astronomers watched in 2010 was decades of stored internal energy releasing in a matter of weeks. If Saturn had a solid surface to stand on, it does not. But follow the thought. The sky during this storm would have been incomprehensible. The convective towers reaching up from the water cloud layer 125 to 250 kilometers below the visible tops would have been producing lightning bolts of a scale that illuminate cloud regions 200 kilometers across. Not a flash that lights up the sky for a fraction of a second. A discharge that illuminates a region of atmosphere roughly the size of Cuba, repeatedly 10 times a second. The thunder would never stop. The pressure waves from convection alone would have shaken anything within range. The sheer electrical noise produced by this system would have made radio communication across the entire planet essentially impossible. Months after the storm's peak activity, Cassini continued tracking the aftermath. The upper atmosphere retained thermal anomalies long after the visible convection subsided. Chemical composition at the cloud tops had shifted. The equatorial disturbances the storm had triggered persisted. Saturn's atmosphere does not simply reset after an event like this. It carries the record of it forward, altered in ways that slowly fade but do not immediately disappear. What the 2010 storm demonstrated was the degree to which Saturn's exterior is a product of its interior. The cloud bands, the jet streams, the pale orderly appearance of the planet from a distance. None of that is the real story. The real story is whatever is happening thousands of kilometers down, where heat accumulates under pressure we cannot directly measure, following timelines we cannot fully predict, building toward events that remake the visible atmosphere in a matter of weeks. When the storm finally faded months later, it had left permanent scars in Saturn's upper atmosphere detectable for years. Had briefly released more energy than models said the planet should have been able to produce. The most powerful lightning bolt ever recorded on Earth released enough energy to power a home for several months. Scientists measured it, documented it, and it made the news. By Saturn's standards, that bolt was unremarkable. It would not have registered as unusual in any storm Saturn has ever produced. The gap between what Earth calls extreme electrical activity and what Saturn generates routinely is not a matter of degree. It is a matter of category. Individual lightning bolts on Saturn release up to 8 billion joules of energy. A single discharge. Earth's most powerful lightning events, the rare ones that researchers track specifically because of their exceptional energy, reach a few billion joules at the upper limit. Saturn's average storm lightning runs roughly 10,000 times more energetic than what a typical thunderstorm here produces. Those are not numbers that are easy to hold in your mind. 10,000 times. The storm that was documented in 2011 generated more than 10 lightning flashes per second at peak intensity. Not one, not two, 10 per second, each one carrying energy that would dwarf anything in Earth's meteorological record. To understand what a Saturnian lightning bolt actually looks like, start with what you already know. When lightning strikes near you on Earth, there is a brief flash. The illuminated region, the cloud lit from inside, might span a few hundred meters. That is the visual scale of terrestrial lightning. A Saturnian lightning bolt illuminates a cloud region roughly 200 kilometers in diameter, not 200 meters. 200 kilometers. That is a circle of cloud larger than some countries, lit from the inside by a single electrical discharge. The flash does not snap and vanish the way Earth's does. It lasts longer, burns brighter, and the area it lights up is operating at a completely different physical scale. This happens because of where the lightning originates. On Earth, lightning forms in the middle layers of storm clouds, where ice particles and water droplets interact in ways that separate electrical charge. On Saturn, the lightning is generated 125 to 250 kilometers below the visible cloud tops, deep in the water cloud layer where water condenses in an atmosphere of hydrogen and helium under pressures that make the process almost unrecognizable. At that depth, the pressure is enormous. The convective forces driving the thunderstorm dynamics, the rising columns of hot gas, the sinking columns of cool gas, are operating at scales that nothing in Earth's atmosphere approaches. The storm cells feeding these lightning events extend far deeper than any terrestrial thunderstorm could. What we see as bands and white spots at the cloud tops is the surface expression of convective violence happening hundreds of kilometers below. The optical power output of the 2011 storm's lightning reached approximately 10 billion watts, measured continuously over the life of the event. 10 billion watts of optical power means 10 billion watts of light being produced by electrical discharges, continuously, as the storm raged. That figure is so far outside the range of anything terrestrial meteorology deals with that it barely connects to familiar reference points. A large city might consume a few gigawatts of electrical power at peak demand. The lightning in the 2011 Saturn storm was producing that much light output, not electrical energy total, but light specifically, as a continuous emission. Here is where something strange enters the picture. All of this, the scale, the frequency, the energy, was not discovered by watching the lightning directly. We have never seen a Saturnian lightning bolt with an optical telescope. The reason is that the bolts originate so deep in the atmosphere that by the time the light has scattered through 125 to 250 kilometers of dense gas and cloud layers, it is diffused. The upper atmosphere absorbs and disperses the optical signal before it escapes into space at any intensity that a telescope could resolve as a distinct flash. From the outside, Saturn does not flicker the way a distant lightning storm looks from a plane window at night. The light is swallowed. What does escape is radio. Lightning generates intense bursts of radio frequency radiation. and Saturn's atmosphere is far less opaque to those wavelengths than to visible light. Cassini detected these radio bursts clearly. Scientists call them Saturn electrostatic discharges, and Cassini recorded them throughout its mission, logging storm events, measuring their frequency and intensity, and tracking how activity rose and fell during the 2010 and 2011 storm cycle. The radio signature of each discharge is distinctive and measurable, and from those signals, researchers reconstructed the energy estimates, the flash rates, and the storm timelines. Everything known about Saturnian lightning was built from electromagnetic inference, not direct observation. That is worth sitting with. One of the most violent electrical phenomena in the solar system has never been directly witnessed. The numbers describing it come from instruments picking up radio waves, not cameras capturing light. The storm that produced 10 flashes per second and 10 billion watts of optical power is known entirely through its echo in the electromagnetic spectrum. There is no photograph of a Saturn lightning bolt. There is no frame of video. There is data, and from that data, calculations, and from those calculations, a picture that is striking precisely because it was assembled without anyone ever seeing the thing itself. The 2010 storm produced hundreds of radio bursts per second at some point during its peak. The earlier Southern Hemisphere storms Cassini observed, in the years before the Great Northern Storm developed, were already registering as extreme events. They were producing individual flashes, with optical energies reaching 8 billion joules. Those storms were considered remarkable. The 2011 event raised the scale further. Every flash on Saturn is releasing energy that would classify as extraordinary by the standards of any storm system our planet has ever produced, and we have never actually seen one directly, only heard it. Saturn's core is hotter than the surface of the Sun, not warmer, not comparable, hotter. The Sun's visible surface runs at about 5,800 Kelvin. Saturn's core sits at roughly 10,000 Kelvin, nearly twice that. This is not a rounding error or a modelling artifact. It is the result of direct measurement, confirmed by spacecraft and independently verified through multiple detection methods. A planet more than 1 billion kilometers from the Sun is carrying more heat in its center than the nearest star has on its face. To understand why this is the case, you have to go back 4.5 billion years. Saturn did not form gently. It formed through collision, a prolonged violent accretion process in which chunks of rock and ice and gas slammed into one another at tremendous velocity, building up mass over millions of years. Every collision converted kinetic energy into heat. The faster the impact, the more heat released. When the pieces were small, that heat bled off quickly into space. But as Saturn grew larger and more massive, the outer layers began trapping the heat generated deeper inside. The planet became its own insulator. The gas surrounding the core is so thick, so deep, and so massive that it acts like a blanket hundreds of thousands of kilometers thick. Heat cannot escape quickly through that much mass. Aerial. It radiates outward slowly, over timescales that stretch into billions of years. And even after 4.5 billion years of cooling, the core is still burning at 10,000 Kelvin. This alone would be remarkable. But there is a second process running alongside it, and in some ways it is stranger than the first. Saturn is made mostly of hydrogen and helium. These two gases did not stay evenly mixed. Helium is denser than hydrogen, and over time, helium droplets began forming and sinking through the hydrogen layers toward the core. This is happening right now. Deep inside Saturn, at this moment, helium is falling. Not quickly, the descent happens over millions of years, but it is continuous and ongoing. As the helium sinks through hundreds of thousands of kilometers of planetary material, gravity converts that motion into heat. The falling helium is essentially releasing gravitational potential energy, and that energy has nowhere to go except into the interior. It becomes heat. Saturn is generating energy through its own internal differentiation, a slow-motion gravitational engine that has been running for billions of years and shows no sign of stopping. The result of these two processes combined is measurable from Earth. Saturn radiates approximately 2.3 times more energy outward than it receives from the Sun. Scientists confirmed this through direct thermal measurements made by spacecraft. The number has been independently checked, and it holds. Saturn is not reflecting slightly more energy than it takes in. It is radiating more than twice as much. The excess has to come from somewhere, and the somewhere is the interior, the stored heat from formation, the ongoing helium rain. These two sources together account for why Saturn is glowing in the infrared, bleeding energy into space at a rate that dwarfs anything sunlight could explain at that distance. To put that in context, the Sun delivers roughly 1% as much energy to Saturn as it delivers to Earth, because Saturn is nearly 10 times farther away and light intensity falls off with the square of distance. Yet Saturn's atmosphere is violently active. Its winds move at 1,800 kilometers per hour. Its storms grow to continental scale within days. Its lightning releases billions of joules per bolt. None of this can be driven by sunlight. Almost all of it traces back to the internal heat engine. The terrifying things happening in Saturn's atmosphere, the things described in the previous sections, are powered by this. The furnace at the core is what drives the machine at the surface. There is something difficult to hold in your mind about this. Saturn has been cooling for 4.5 billion years. Earth did not exist for the first several 100 million years of that cooling period. Life on Earth took another few billion years to produce anything complex. Entire species appeared and vanished. Continents drifted. Ice ages came and went. Mountains rose and eroded, and through all of that, Saturn's core was steadily, slowly shedding heat. It was already ancient when the first fish appeared on Earth. It has been running this furnace since before the planet you are standing on had oceans, and it is still going. The helium rain has not stopped. The stored heat from formation has not fully dissipated. The thermal output is not declining on any timescale that matters to human civilization, or to any plausible timeline of human existence. The models that describe this process project it running for billions of years more, through whatever happens to Earth, through the eventual expansion of the Sun, through the final stages of the inner solar system's existence. Saturn is not hot in the way a fire is hot, something that burns brightly and then goes out. It is hot in the way a planet-sized thermal reservoir is hot, deep, slow, self-sustaining, and operating on timescales so long that the word ancient barely applies. The lightning, the storms, the winds, those are all symptoms. The core is the source. It has been since before any of the geology of this planet began. The process that keeps it burning has been running for 4.5 billion years and will continue long after Earth is gone. Below Saturn's visible cloud layers, there is a substance that does not exist naturally anywhere on Earth. To understand what that means, you have to follow the pressure downward. At the cloud tops, Saturn's atmosphere is thin and cold, ammonia crystals drifting through temperatures that would freeze a person solid in minutes. But descend deeper and everything changes. The pressure builds with every kilometer. The gas thickens. The temperature climbs. This is not a gradual shift in the way Earth's atmosphere becomes denser closer to the ground. This is a compression so extreme that the rules governing ordinary matter start to break down. By the time you have descended roughly 2,000 kilometers below the visible cloud tops, the hydrogen around you is no longer behaving like a gas at all. The pressure is high enough that it has been forced into a liquid state. Not water, not anything with a familiar name, just hydrogen, squeezed so hard that it flows. Most people stop there because liquid hydrogen is already strange enough. But the interior does not stop there. Keep descending. The pressure continues climbing. The temperature rises past anything a laboratory instrument can easily sustain. At somewhere around 2 million times the pressure of Earth's sea level atmosphere and roughly 6,000 Kelvin, something happens that has no equivalent in nature anywhere on Earth. The hydrogen undergoes a phase transition. The electrons that were orbiting individual hydrogen atoms get stripped away. They stop belonging to any particular atom. They become free, moving through the material the way electrons move through copper wire. The hydrogen has become electrically conductive. It generates and carries electrical current. It flows like a liquid, but behaves like a metal. Scientists call this liquid metallic hydrogen, and it is one of the most exotic states of matter known to physics. It exists inside Saturn right now, in a layer that extends thousands of kilometers through the plan. Its interior, and it has been sitting there for 4.5 billion years. This is not theoretical in the way some interior models are. The evidence for it is indirect but strong. Saturn has a magnetic field, and something has to generate that field. Magnetic fields on planetary scales are produced by electrically conductive fluids moving in organized patterns, the same basic process that generates Earth's magnetic field in our liquid iron outer core. Saturn's metallic hydrogen layer is its equivalent of that outer core, a vast ocean of conducting fluids set in motion by the planet's rotation and internal heat. Every time Cassini measured Saturn's magnetic field, every contour and anomaly in that data was reflecting the behavior of this impossible material deep inside the planet. Above the metallic hydrogen layer sits a region of liquid molecular hydrogen. The hydrogen there is still liquid under the intense pressure, but the electrons have not yet been stripped free. The atoms are still intact, just densely packed and flowing. Between this layer and the metallic hydrogen below, there is no sharp boundary you could point to and say, here is where one ends and the other begins. The transition is gradual, conditions shifting continuously with depth. At the very center of all of this is a core. Scientists estimate it is composed of rock, metal, and compressed ice, though ice is almost a misleading word for it at these conditions. The pressures at Saturn's core are so extreme that water, methane, and ammonia exist in states that behave more like viscous fluids than anything you would recognize as ice. The core's temperature, as covered in the previous section, exceeds the surface of the Sun. The pressure at its boundary is many millions of times Earth's atmosphere. Nothing we have built could survive it for a fraction of a second. Here is something worth holding on to. If you were somehow descending through Saturn, you would never cross a distinct boundary from atmosphere into interior. There is no door, no transition point where the sky ends and the planet begins. Deep enough in Saturn's atmosphere, hydrogen exceeds what physicists call its critical point, the conditions past which gas and liquid become thermodynamically indistinguishable. Below that depth, the question of whether you're inside a gas or a liquid stops having a meaningful answer. The substance simply gets denser around you, hotter around you, more pressurized around you, continuously. By the time the material around you is conducting electricity like a wire, glowing faintly with its own heat, you would have no memory of having crossed a surface. There was no surface to cross. This is fundamentally different from anything in human experience. Even at the bottom of Earth's ocean, you are still inside something you could describe cleanly as water. Saturn offers no equivalent clarity. The material transitions from gas to liquid to metallic conductor without interruption across thousands of kilometers under conditions that would vaporize any probe we have ever built within seconds of entry. The problem of studying Saturn's interior is that nothing can go there. No instrument survives the descent long enough to reach the interesting layers. The Cassini spacecraft spent 13 years orbiting Saturn and learned an enormous amount about its magnetic field, gravitational harmonics, and ring interactions. From those measurements, researchers inferred interior structure the way a geologist infers what lies underground from seismic waves, not by seeing it directly, but by reading the signals it produces. Laboratory experiments can briefly create pressures approaching metallic hydrogen conditions for milliseconds in very small volumes. Those experiments have confirmed that the transition is real and happens at roughly the conditions the models predict. But briefly and small are doing a lot of work in that sentence. Everything we know about what lies in those depths comes from equations, inference, and brief flashes in laboratory experiments, not from any instrument that has ever been there. The rings of Saturn look solid in photographs. That impression is one of the most persistent illusions in all of astronomy. From a telescope, from a spacecraft image, from every iconic photograph ever taken, the rings appear to be a flat, continuous disk of material, almost like a vinyl record wrapped around the planet. They are not that. Understanding what they actually are changes the entire picture. Start with the dimensions. The rings span roughly 270,000 kilometers from their inner edge to their outer edge. That is about 2/3 of the distance from Earth to the Moon. If you stretched the rings out and held them next to the Earth-Moon system, they would reach nearly all the way across. In terms of raw width, they are staggering. But here is the number that stops people cold. The average thickness of Saturn's rings is about 10 meters. 10 meters. That is the height of a 3-story building, a structure wider than the distance to the Moon, and 10 meters thick. The ratio of width to thickness is more extreme than a sheet of paper. It is more extreme than a razor blade. It is one of the most extreme aspect ratios of any naturally occurring structure in the solar system. If you look at the rings from the side, edge on, they essentially disappear. Cassini photographed Saturn from certain angles where the rings vanished almost entirely, reduced to a faint line crossing the planet's disk. So what is actually in there? The rings are not solid material. They are not a surface anyone could land on. They are made of billions of individual particles, spread out across that enormous disk, each one in its own orbit around Saturn. The particles range from microscopic grains of dust to chunks of ice the size of houses. Some are smaller than a grain of sand. Some are larger than a car. A small fraction are genuinely large, the size of a small building. They are not touching each other in any continuous sense. The rings are mostly empty space, with particles separated by gaps, orbiting at slightly different velocities depending on their distance from Saturn. The composition is primarily water ice, the same material that makes up glaciers and frozen lakes, but with minor amounts of silicate rock and organic compounds mixed in. This is why the rings are so reflective. Ice is bright. Saturn's rings reflect sunlight efficiently, which is part of why they are visible at all from Earth. The rings are not opaque. Starlight passes through them. Spacecraft have flown through the ring plane and emerged on the other side without being destroyed, though not without encountering particles. Cassini flew between Saturn and its innermost ring during its final mission phase, in a gap roughly 2,000 kilometers wide, and recorded what it encountered. The particle density in that gap was lower than expected, but not zero. Nothing about this system is empty in any absolute sense. And the rings are not peaceful. Each particle is traveling at orbital velocity, and orbital velocity is not slow. A particle in the inner rings moves at roughly 17 kilometers per second relative to an outside observer. The outer rings move more slowly, around 15 kilometers per second. Particles at different distances are therefore moving at different speeds, meaning two particles at slightly different distances are in constant relative motion. Collisions happen continuously. These collisions are low velocity by the standards of planetary physics, but they are not gentle. Over billions of years, this constant grinding has pulverized particles, rounding them and slowly reducing their size. From the outside, things are even more violent. Micrometeoroids, tiny rocks drifting through the solar system, hit the rings constantly at hypervelocity. When a fast-moving particle from interplanetary space strikes a ring particle at several kilometers per second, it does not simply bounce. It vaporizes on impact and launches a cloud of ejecta in all directions. Some of that ejecta escapes, some of it falls back, some of it goes into different orbits. This process has been churning through the ring material for as long as the rings have existed, and it has been changing them the entire time. Not all of the rings are the same age or the same origin. The main rings, labelled A, B and C from the outside in, are the dense, bright structures most people picture. Beyond them are fainter rings with different compositions and histories. The outermost E ring is the widest and most diffuse, and it is actively fed by material from Enceladus. Every time Enceladus fires one of its geysers into space, some of that water vapor and ice falls into the E-ring's orbit and replenishes it. Without Enceladus, the E-ring would thin and disappear. It is not a remnant but a living structure, being fed continuously by a geological process happening right now on a moon 500 kilometers across. The question of where the main rings came from has not been fully settled. There are two broad categories of explanation. Either the rings are primordial, forming from material left over when Saturn formed 4.5 billion years ago, or they are much younger, the product of a more recent catastrophe. The younger origin story is the one that has gained traction in recent years. The rings may be only around 100 million years old. In solar system terms, that is recent. Dinosaurs were still alive on Earth when Saturn's rings may have formed. The proposed mechanism is straightforward in its violence. A moon, somewhere in the size range of a medium-sized icy satellite, drifted too close to Saturn. Saturn's tidal forces, the same gravitational differential that drives Enceladus's geysers, overwhelmed the gravity holding the moon together. The moon came apart. Its material spread into a disk around Saturn's equator, and over time, the collisions and orbital dynamics organized that material into the structures we see now. The moon is gone. There is no surviving fragment that can be identified. The most beautiful structure in the solar system is the debris field of a moon that Saturn tore apart, and it is slowly grinding itself down to nothing. Saturn's rings are disappearing. Not on any timescale you need to worry about in your lifetime, or your grandchildren's lifetimes, or 10,000 generations from now, but disappearing all the same, steadily, continuously at this moment, as material from the most famous structure in the solar system falls inward toward the planet and burns up. The rings that have defined Saturn in every photograph, every telescope view, every painting of the outer solar system are not a permanent feature. They are a temporary one, and the process that is removing them has been measured directly. The mechanism is not a single thing. Several processes are working on the rings at once, each pulling material inward by a different route. The first is ionization. Ultraviolet light from the sun and plasma circulating in Saturn's magnetosphere strike ring particles and strip away electrons. Water ice, which makes up the bulk of the rings, is particularly vulnerable to this. Once a particle becomes ionized, it is no longer neutral. It picks up an electrical charge, and charged particles in a magnetic field do not stay where they are. Saturn's magnetic field lines reach out through the ring plane, and ionized particles get dragged along those lines, down towards Saturn's upper atmosphere. They follow the field like water following a pipe. The pipe runs from the rings to the planet, and there is no valve. The second process is more mechanical. Ring particles are not static. They orbit Saturn at different speeds depending on how far out they are. Particles closer to Saturn move faster. Particles further out move slower. Over time, several forces nudge ring particles towards slightly lower orbits. Orbital decay, radiation pressure, the Poynting-Robertson effect, which is the slow drag produced when a particle absorbs sunlight and re-emits it as heat in a way that is not perfectly symmetric with its direction of travel. It is an incredibly small force, but it acts continuously over millions of years, and it pulls particles inward. Slowly, persistently, they spiral down. Cassini measured what happens when they arrive. Ring material falls into Saturn's upper atmosphere at a rate of roughly a ton per second. 1 ton of ring material every second raining into the planet. That number was not guessed. It was measured using instruments on Cassini that detected the chemical signature of ring particles entering the ionosphere at specific latitudes, tied directly to the magnetic field lines running back up to the ring plane. The material comes in moving faster than the atmosphere below it, the same way a satellite re-entering Earth's atmosphere is moving faster than the air it plunges into. The energy released by that speed difference is real and detectable. It disrupts the local chemistry. It changes the electrical properties of the ionosphere at the exact latitudes where the field lines touch down. James O'Donoghue first noticed evidence of this from Earth. Dark bands appeared in Saturn's ionosphere at latitudes that matched the magnetic footprints of the denser, waterier sections of the rings. The brightest, most water-rich rings were producing the most visible chemical disruption in the atmosphere below. The correspondence was precise enough that it could not be coincidental. What the rings were doing to the ionosphere was being read back as a pattern from 1.4 billion kilometers away. Cassini then confirmed it in detail, flying through the region between the rings and the planet in its final months and measuring the infall directly. The effect on the atmosphere is specific. Ring particles are mostly water ice. When water ice arrives in Saturn's upper atmosphere and vaporizes, it releases water molecules that interact with the glowing layer of ionized hydrogen that makes up Saturn's ionosphere. Water is chemically aggressive in this context. It quenches the ionized hydrogen, literally dousing it. The glow dims at those latitudes. What you get are dark bands in the ionosphere, visible from Earth if you know what you are looking at, tracing the invisible architecture of the magnetic field connecting the rings to the planet. At 1 ton per second, the math becomes stark quickly. 1 ton per second is roughly 30 million tons per year. The rings are massive. Estimates put the total mass at around 15 to 40 times the mass of Mimas, one of Saturn's smaller moons. But they are not infinitely massive. At current loss rates, models suggest the rings could be gone within 100 million years. Some estimates are more aggressive. If the infall rate has been higher at certain periods, or if the rate increases as the rings thin and become more exposed to ionizing radiation, the timeline could be significantly shorter. A few tens of millions of years is not an outrageous lower bound. On geological timescales, that is not a long time. There is an additional complication. The rings are also being bombarded by micrometeoroids from outside the Saturn system, tiny rocks hitting ring particles at hypervelocity and kicking material out of the ring plane entirely, either ejecting it into space or sending it on trajectories that end at Saturn. Each of these collisions adds to the slow erosion. The rings are being worn down from above and pulled in from below simultaneously. What this means is that Saturn without rings is not a hypothetical from another kind of universe. It is the future of this one. A few 100 million years from now, something orbiting or passing through this part of the solar system would see a banded planet, pale and large, without the halo that makes Saturn the most recognizable object in the solar system. Whether anything capable of noticing would exist at that point is a separate question. The haze bands would be gone. The ice would be gone. The billions of particles, ranging from dust grains to objects the size of buildings, would have finished their long spiral inward and dissolved into the planet that made them. The most iconic feature in the solar system is temporary, and from Saturn's perspective, the clock is already running. Most people do not think of Saturn as a source of lethal radiation. The rings get the attention. The hexagonal storm gets the attention. The winds and the lightning and the interior heat get the attention. But wrapped around Saturn, invisible to any telescope you would find in a backyard, is a field of high-energy radiation large enough to swallow entire moons, and it already has. Saturn's radiation belts extend from the innermost ring all the way outward to the orbit of Tethys, a moon sitting more than 285,000 kilometers from Saturn. That is a radiation zone wider than the distance between Earth and the Moon. And it is not one belt. There are 6 distinct belts, each carrying protons at different energy levels, each separated from the next, not by empty space, but by the orbits of moons and the physical material of the rings themselves. The rings and moons act as walls. Particles slam into them and stop. Each wall creates a boundary, and each boundary defines a new belt with its own energy signature. The structure is more organized than it sounds, and also more dangerous. Several of Saturn's major moons orbit entirely inside these belts. Janus is in there, Mimas is in there, Enceladus is in there. These are not small objects passing through briefly. They live inside the radiation permanently, circling Saturn while high-energy protons rain into their surfaces continuously. Astronomers have measured the dose rate near Mimas and compared it to the environment near Europa, which orbits inside Jupiter's far more famous radiation belts. The numbers are roughly comparable. Near Europa, the radiation environment is lethal to a human within hours. A dose of around 1,000 rad is enough to kill a person within days at the outside. Some estimates put that timeline in hours depending on exposure. An unprotected person standing on the surface of Mimas would not survive long enough to get a look around. That is not a figure of speech. It is a measurement. What makes Saturn's radiation belts different from Jupiter's is where some of the particles come from. Jupiter's belts are fed primarily by the solar wind, charged particles streaming out from the Sun, caught and accelerated by Jupiter's enormous magnetic field. Saturn's belts do that too, but researchers analyzing the data have found something else. Some of the energetic particles appear to originate from Saturn's own atmosphere and from interactions with the ring material itself. The planet is partially generating its own radiation environment. The rings shed particles. The atmosphere contributes particles. The magnetic field traps them and accelerates them. Saturn is not just sitting inside a radiation field swept in from outside. It is building one. Cassini spent 13 years at Saturn and spent most of that time keeping a careful distance from the worst of the belts. The mission profile was not accidental. Engineers plotted orbits that kept the spacecraft away from the highest energy regions because the accumulated radiation dose would have shortened the mission dramatically, possibly ended it. The instruments were shielded, but shielding only goes so far. For most of those 13 years, Cassini circled Saturn from positions that kept the densest radiation zones between it and the planet, rather than between it and space. Then, at the very end, the mission changed character. In 2017, Cassini executed a series of dives that sent it through the gap between Saturn's innermost ring and the top of the atmosphere, a region nobody had ever explored directly. Scientists expected the radiation there to be severe. The gap between the D-ring and the planet seemed like it should be one of the more hostile environments in the Saturn system, simply because it sits so close to the source of everything else. What they found was something unexpected. The radiation levels in that gap were actually lower than models had predicted. Not low in any absolute sense. The environment was still genuinely hazardous, but lower than expected. The rings above were absorbing particles before they could drift inward. Material that would otherwise be accelerating towards Saturn was being accepted by the ring plane, caught by the billions of particles suspended there, and stopped. The rings, which are slowly eroding into the planet through ring rain, which are losing roughly a ton of material per second to Saturn's atmosphere, are simultaneously acting as a radiation shield. They are a barrier, Charged particles moving through the magnetosphere hit the ring material and are absorbed rather than continuing inward. Without the rings, the radiation environment close to Saturn would be measurably worse. The inner moons, already sitting in a difficult environment, would be in a harder one. The geometry that allows Enceladus and Mimas to exist as distinct objects, rather than simply being scoured down to bare rock by continuous proton bombardment, is partially maintained by the same structures that are themselves dissolving into the planet underneath them. The same rings that are slowly raining down into the planet are also absorbing the worst of the radiation that would otherwise flood the space closer in, which makes what happens when they are gone an interesting question. Titan is larger than the planet Mercury, has a thicker atmosphere than Earth, and its surface is covered in lakes, but none of this is as straightforward as it sounds. Start with the atmosphere. Earth's atmosphere presses down on you at roughly 14.7 pounds per square inch at sea level. Titan's surface pressure is about 1.5 times that. You would feel it, not crushingly. It would not kill you the way Venus's atmosphere would, which runs at 90 times Earth's pressure, but it would be noticeable. The difference is that Earth's atmosphere is mostly nitrogen and oxygen. Titan's is mostly nitrogen and almost nothing else useful. The oxygen is gone. What's left instead is methane, trace amounts of other organic molecules, and a thick photochemical haze that sits in the upper atmosphere like a permanent smog event covering an entire world. Scientists call the compounds in that haze tholins, complex organic molecules built when ultraviolet light from the sun breaks apart nitrogen and methane, and the pieces reassemble into something more complicated. The result is a golden brown ceiling that blocks most visible sunlight from reaching the surface. Standing on Titan, the sun would be a dim smear in a butterscotch sky. You would need a flashlight at midday. The temperature at Titan's surface is around negative 179 degrees Celsius. That number is worth sitting with for a moment. At that temperature, water is not ice in any familiar sense. It is rock. It is harder than most building materials on Earth, and essentially indistinguishable in behavior from granite or basalt. The bedrock of Titan, the stuff that forms cliffs and crater rims and mountain ridges, is frozen water, and the liquid that flows across that bedrock, filling rivers and carving valleys and pooling in vast lakes near the poles, is not water. It is methane. Methane on Earth is a gas. At negative 179 degrees, it is a liquid, and on Titan, it behaves almost exactly the way water behaves on Earth. It evaporates from the surface. It rises into the atmosphere. It condenses into clouds. It rains back down. There is a full methane hydrological cycle running on Titan, mirroring Earth's water cycle so closely that when researchers first started mapping Titan's surface, they kept reaching for Earth-based vocabulary by instinct. River channels, deltas, floodplains, alluvial fans, coastlines. Every one of those features exists on Titan, shaped by flowing liquid, just as they are here. The liquid is simply not water. The Huygens probe landed on Titan in January 2005. It was released from the Cassini spacecraft and spent about 2.5 hours descending through the atmosphere before touching down on the surface. It transmitted for roughly 70 minutes after landing. During the descent, it photographed what appeared to be a drainage network, channels cutting through higher terrain leading down toward a dark, flat plain. When it landed, the surface beneath it had the consistency of wet sand or lightly packed snow. It may have come down near a dry riverbed. The images it sent back looked, in some deeply unsettling way, like somewhere on Earth. Rock-like objects scattered across a flat plain, a hazy horizon, the kind of scene that would be unremarkable on any other world if the rocks were not made of ice, and the haze above was not methane chemistry running at temperatures that kill everything we know of as life. The lakes are real. Cassini mapped them directly using radar. The largest, Kraken Mare, is bigger than the Caspian Sea. There are smaller lakes and seas scattered across the North Polar region, connected in some cases by narrow channels. The Cassini radar data showed them to be smooth, liquid surfaces, and spectroscopy confirmed the composition: liquid hydrocarbons, mostly methane with ethane mixed in. These bodies of liquid have been sitting on Titan's surface long enough to shape the landscape around them. There are wave patterns, or at least the conditions for them. There may be tides driven by Saturn's gravity rather than a moon. Below the surface, the situation shifts again. Tidal forces from Saturn's gravitational pull knead Titan's interior continuously, generating heat. The evidence suggests that somewhere beneath the frozen water crust, a liquid water ocean exists, kept liquid not by solar warmth, which barely reaches this far out, but by that internal tidal friction. This ocean has never been seen directly, but Titan's response to Saturn's tidal pull is more flexible than a purely solid body would produce, and that flexibility points toward a liquid layer somewhere in the interior. If that ocean is real, Titan has liquid water underground and liquid methane on the surface simultaneously. Two different kinds of liquid, two entirely separate systems operating on the same world. Some researchers have proposed that Titan's surface chemistry is rich enough that something could theoretically use liquid methane as a solvent the way Earth life uses water, a completely different biochemistry built around different molecules, running at temperatures 200 degrees colder than anything alive on Earth. There is no evidence this is happening. There is no observation that points toward biology in Titan's methane lakes. But the organic chemistry is genuinely complex. Cassini detected hundreds of distinct organic compounds in the atmosphere. The building blocks for complicated molecules are everywhere. Whether any of that chemistry climbs towards self-replication under those conditions is a question nobody can answer yet. What is not in question is the landscape. Wind-driven dunes of dark organic material stretch across Titan's equatorial regions, each one built from particles that rained down from the atmosphere over millions of years and were then pushed into ridges by slow methane winds. These dunes are hundreds of meters tall and hundreds of kilometers long. Titan's equator looks, from orbit, like a desert, except the sand is not silicate. It is the chemical byproduct of a sky full of tholins, slowly falling, slowly accumulating, slowly being sculpted by a wind that moves at walking pace but has been blowing for a very long time. Every landscape feature that resembles something familiar on Earth is filled not with water but with liquid methane at temperatures that would freeze a human body rigid in minutes. Enceladus is small enough to fit inside a single US state, and it is actively spraying water from a global ocean into space at this moment. The Moon is 504 kilometers across. For comparison, the state of Arizona stretches roughly 660 kilometers at its widest point. Enceladus would fit inside it with room to spare. By every measure of size, this is an unremarkable object, a small frozen ball of ice orbiting a gas giant in the outer solar system. Nothing about its dimensions suggests it should matter, and yet it is one of the most scientifically significant objects astronomers have ever found, because what is happening inside it does not match what something this small is supposed to be capable of doing. The geysers are where the story starts. At Enceladus's south pole, there are roughly 100 distinct jets of water vapor and ice particles firing continuously into space. They reach hundreds of kilometers above the surface. The material they eject is not recycled back down. Most of it escapes Enceladus's gravity entirely and feeds directly into Saturn's E-ring, the broad, diffuse outermost ring. Enceladus is not just releasing material, it is actively constructing one of Saturn's rings in real time. That ring would not exist without this moon's interior doing something it has no obvious right to be doing. The energy source behind all of this is tidal heating. Saturn is massive. Enceladus orbits close enough that Saturn's gravity pulls at it unevenly, The near side of the Moon feels a stronger gravitational tug than the far side. This differential force constantly flexes the interior of Enceladus, compressing and stretching it on each orbit, and that mechanical stress converts directly into heat. The same process drives volcanic activity on Io, Jupiter's innermost large moon. On Io, it produces hundreds of active volcanoes. On Enceladus, it keeps an ocean liquid underneath roughly 30 to 40 kilometers of ice, in a place where the surface temperature hovers around -200 degrees Celsius. Cassini confirmed that ocean is real. Not inferred, not modelled, confirmed. The spacecraft flew multiple times directly through the plumes erupting from the South Pole and sampled them. Water vapor, sodium salts, silica nanoparticles, molecular hydrogen, organic molecules. The sodium salts alone were significant. Dissolved salts in water require liquid water sitting in contact with rock for extended periods. That is not a surface phenomenon. That is a deep ocean floor chemistry signal. The silica nanoparticles told the same story in a different way. Silica particles of that specific size form when hot water interacts with rock at high temperature and then cools rapidly as it rises. On Earth, that process happens at hydrothermal vents on the ocean floor. Enceladus appears to have hydrothermal vents at the bottom of its ocean, roughly 30 to 40 kilometers beneath the surface of a moon 504 kilometers across in the outer solar system, at a distance from the Sun where the temperature of space itself would freeze any exposed water solid in seconds. This is worth sitting with. Hydrothermal vents on Earth exist in complete darkness, under enormous pressure, cut off from sunlight entirely. They support ecosystems, tube worms, bacteria, crustaceans, fish, entire food webs built on chemical energy rather than solar energy. The chemistry Cassini detected in Enceladus's plumes matches the chemical environment around those vents almost component by component. Water, heat, organic molecules, minerals dissolved from rock, molecular hydrogen, which specific types of microorganisms on Earth use as an energy source. Whatever checklist astrobiologists use to define the basic requirements for life, Enceladus checks every box. The ocean has probably been liquid for hundreds of millions of years. That is a long time, long enough by Earth standards for something to get started. Now here is the problem. Enceladus does not orbit Saturn in open space. It orbits Saturn inside the radiation belts. Specifically, it orbits within a region where high-energy protons are continuously bombarding everything in the vicinity. The radiation dose at the surface of Enceladus is comparable to the dose rate near the surface of Europa, Jupiter's moon, which is itself considered one of the most hostile radiation environments in the solar system. Around 1000 rad is a lethal dose for a human being. Delivered over hours to days, the surface of Enceladus would deliver that. An unprotected person standing on the ice would be dead from radiation exposure before most other environmental hazards had time to matter. For surface life, this is disqualifying. Nothing we know of could survive on the exterior of Enceladus. But the question is not about the surface. The ocean is below 30 to 40 kilometers of ice. Radiation does not penetrate water and ice efficiently at those depths. The ice itself is a shield. Whatever is down there, if anything is down there, is physically separated from the radiation environment above by tens of kilometers of frozen water. The radiation belts are a problem for anything trying to survive on the outside. They may be irrelevant to anything surviving on the inside. This creates a situation that is genuinely without parallel anywhere else in the solar system. A moon small enough to misplace, orbiting inside one of the most radiation-intense environments outside of Jupiter's system, actively venting material from a liquid water ocean that contains the chemical signatures of hydrothermal activity, and we cannot get to the ocean to check. The ice is too thick for any instrument we have yet designed. Cassini flew through the plumes and found chemistry that pointed at life's ingredients, but it could not find life itself because it was not built to. The next missions targeting Enceladus will carry more sensitive instruments. Whether they will be sensitive enough is another question entirely. The most promising place for life in the outer solar system sits inside Saturn's radiation belts, which means whatever might be living under that ice is already surviving conditions that would kill most life on Earth. Saturn's magnetic field is 578 times stronger than Earth's, and nearly perfectly aligned with its rotational axis, which according to standard theory is not supposed to be possible. Every other planet with a significant magnetic field has that field tilted relative to its spin axis. Earth's magnetic poles are offset from its geographic poles by roughly 11 degrees. Jupiter's magnetic field is tilted by about 10 degrees. This is expected. The standard dynamo model, the physics that explains how rotating, electrically conductive fluids generate magnetic fields, essentially requires some tilt. A perfectly aligned field should not sustain itself. It should decay. Saturn's field has been measured repeatedly by Pioneer 11, by Voyager 1, by Voyager 2, and in extraordinary detail by Cassini over 13 years of orbital observation. The tilt is less than 1 degree. By the standards of planetary physics, that is 0. No one has a clean explanation for this. The leading theory is that a layer of electrically conductive fluid sits above the metallic hydrogen interior and acts as a kind of filter, suppressing the non-axisymmetric components of the field before they escape the planet. Essentially, something inside Saturn may be smoothing out the field as it rises outward, leaving only the perfectly aligned component visible from outside. This is mathematically plausible. It is not proven. It is the best explanation available, and it still requires Saturn to have a very specific internal structure that has not been directly confirmed. The magnetic field of Saturn is a measurement that planetary science has had for decades and still cannot fully account for. The field itself is generated deep in Saturn's interior, in the liquid metallic hydrogen layer that sits below roughly 30,000 kilometers of compressed molecular hydrogen. In that region, hydrogen atoms are compressed so tightly that electrons move freely between them, turning the material into an electrically conductive fluid. As Saturn rotates, once every 10.5 hours, that fluid moves, and moving electrical conductors generate magnetic fields. The heat rising from the core drives convective flows in this layer, creating the organized circulation patterns that sustain the dynamo. Saturn has been doing this for 4.5 billion years without stopping. The magnetosphere that results is enormous. Toward the Sun, it extends roughly 1 million kilometers before the solar wind pushes it back. On the downwind side, the tail of the magnetosphere stretches tens of millions of kilometers into the outer solar system. Everything inside that volume is dominated by Saturn's magnetic influence, rather than the direct flow of the solar wind. The radiation belts sit inside this magnetosphere. The rings sit inside it. Every one of Saturn's major moons orbits inside it. The magnetosphere is not background infrastructure. It is the environment that everything in the Saturn system lives inside. What makes Saturn's magnetic field genuinely unusual is how physically connected it is to the rest of the system. The field lines do not just sit there passively. They thread through the rings, through the ionosphere, and out to the orbiting moons. Charged particles, ions and electrons, follow these field lines the way water follows a channel. Ring particles that get ionized by ultraviolet light or by collisions with magnetospheric plasma do not simply float there. They couple to the magnetic field and get pulled along it, drawn down into Saturn's upper atmosphere at the specific magnetic latitudes where those field lines intersect the planet. That is ring rain. The rings are not draining into Saturn randomly. They are draining along organized magnetic pathways, and the location where material arrives in the atmosphere is determined by the geometry of the field itself. This is why the dark bands that O'Donoghue identified in Saturn's ionosphere align precisely with the magnetic field lines that connect to the densest parts of the rings. The same mechanism operates with the moons. Enceladus, sitting deep inside the radiation belts, is constantly spraying water vapor and ice particles from its south polar geysers. A significant fraction of that material gets ionized and enters the magnetosphere, loading it with fresh particles. These particles then travel along field lines, interacting with the rings and the atmosphere in ways that Cassini spent years trying to fully map. The moon is feeding the magnetosphere. The magnetosphere is shaping the radiation environment around the moon, and the rings are caught in the middle, conducting material along field lines down to the planet. Saturn's magnetic field is the invisible architecture that connects the rings to the atmosphere, the moons to the radiation belts, and the whole system to the flow of material that is slowly but continuously remaking Saturn from the outside in. Jupiter is the largest planet in the solar system, and it gets most of the attention. It's bigger than every other planet combined. Its great red spot has been spinning for centuries. It has the most powerful radiation belts in the solar system, a magnetosphere that stretches past the orbit of Saturn, and a mass so large that some astronomers half-jokingly call it a failed star. Jupiter is impressive in a way that hits you immediately, the way a large building hits you. You understand it at a glance. Saturn does not work that way. Start with the winds. Jupiter's atmosphere moves fast. Measured jet streams in Jupiter's cloud layers reach around 600 kilometers per hour, which would obliterate anything standing on a solid surface. Saturn's equatorial winds top out near 1,800 kilometers per hour. That is not a small margin. That is 3 times faster, maintained continuously, across a planet nearly as large as Jupiter. The gap is especially strange, given that Saturn is further from the Sun and receives a fraction of the solar energy Jupiter does. Jupiter's winds, at least in part, can be attributed to its size and solar input. Saturn's cannot. The energy is coming from somewhere else, somewhere internal, and the fact that it produces winds faster than Jupiter's despite receiving less energy from outside is the kind of number that does not resolve cleanly. Then there is the storm comparison. Jupiter's great red spot is famous. It has been documented for at least 350 years. It is a hurricane roughly the size of Earth, and it has survived longer than any storm system in recorded observation. That is genuinely remarkable. But it is still a storm. It is oval, it rotates. It behaves the way large atmospheric vortices behave in fluid dynamics textbooks. Saturn's polar hexagon follows none of those rules. A 6-sided geometric structure, each wall longer than Earth's diameter, maintaining perfect angular symmetry for decades, with wind speeds of 300 kilometers per hour along each edge. The fluid dynamics that allow this to form require conditions so specific that no other planet in the solar system has managed to replicate them. Jupiter has no hexagon. Saturn's hexagon has no real explanation that fully satisfies the question of why it stays so stable for so long. The rings are another comparison that goes further than it looks. Jupiter has rings. Most people don't know this. They are thin, dark, made mostly of dust, and almost invisible unless you're looking for them. Saturn's rings are vast, brilliant, and made of billions of ice particles spanning 270,000 kilometers. That comparison is already striking. But the deeper point is that Saturn's rings are falling into the planet right now. They are raining down at roughly a ton per second. They are interacting with Saturn's magnetic field, altering the chemistry of the ionosphere, leaving dark bands at specific latitudes. They may be entirely gone within 100 million years. Jupiter's rings are not doing any of this. They are background features. Saturn's rings are active participants in a process that is slowly dismantling one of the most famous structures in the solar system. Jupiter's radiation belts are stronger. That is real. The environment around Jupiter is more immediately lethal than the environment around Saturn. Jupiter wins on raw radiation intensity, but Saturn's radiation belts contain Enceladus, a moon with a global liquid water ocean, hydrothermal vents on the seafloor, and a chemical signature in its plumes that looks remarkably consistent with conditions where life on Earth arose, and it orbits inside a radiation belt that would kill an unprotected person in hours. Jupiter's moons are scientifically interesting, but none of them combine biological plausibility and environmental hostility in the same space the way Enceladus does. Europa is outside the worst of Jupiter's belts. Enceladus is inside Saturn's. The contradiction there is sharper. Jupiter has no Titan. This matters. Titan is larger than Mercury. It has a denser atmosphere than Earth. It has river channels, lakes, and sand dunes. It rains methane. Its bedrock is frozen water. The surface temperature sits around -179 degrees Celsius. Every landscape feature that looks familiar is filled with cryogenic hydrocarbon instead of water. Titan is not just a moon. It is a world running a parallel version of Earth's hydrological cycle on entirely different chemistry. Jupiter has no equivalent. Ganymede is large, Callisto is ancient, Io is volcanic. None of them are running alien weather systems over alien seas. The deeper argument is this. Jupiter is extreme in proportion to its size. It is large, so its gravity is powerful. It is large, so its storms are vast. It is large, so its magnetic field is strong. Every extreme thing about Jupiter makes sense once you accept how large it is. Saturn does not work that way. Saturn's density is lower than water. Its magnetic field is almost perfectly aligned with its rotational axis, which standard dynamo theory says should not happen. Its internal heat output is high enough to drive winds 3 times faster than Jupiter's, despite receiving far less solar energy. It generates internal heat through helium sinking through hydrogen in a process that is still active after 4.5 billion years. Its polar storm is a geometric structure that should not persist. Its rings are active, complex, dying. Its moons contain oceans inside radiation belts. These are not features that scale with mass. They are features that require separate explanations, and several of those explanations are still incomplete. Jupiter is violent because of what it is. Saturn is strange in ways that cut deeper than size alone. Saturn is far enough away that none of what we have talked about so far poses any direct danger to anything on Earth. It sits roughly 1.4 billion kilometers out, and at that distance its winds and lightning and hexagonal vortex are genuinely no threat to us. But there is a thought experiment worth running, because the numbers that come out of it are clarifying. They show something that a list of individual facts cannot quite capture on its own. The forces operating inside the Saturn system are not just unusual. They scale in ways that become catastrophic the moment you close the distance. Start with what you would see. If Saturn occupied the same orbital position as Earth, the rings would span an arc across the night sky measurable in tens of degrees. For comparison, the full moon covers about half a degree. Saturn's rings at Earth's orbital distance would stretch across roughly 35 degrees of sky, edge to edge, visible during the day, casting shadows at night. That part is almost beautiful. The rest is not. Tidal forces scale with the inverse cube of distance. The moon is about 384,000 kilometers away, and its tidal pull is enough to raise Earth's oceans by roughly a meter, drive coastal flooding cycles, and exert a slow but measurable stress on the crust itself. Saturn is 95 times more massive than Earth. At Earth's orbital distance, Saturn's tidal force on our planet would be approximately 400 times stronger than the moon's. The oceans would not just have tides, they would be perpetually deformed into enormous standing waves, with bulges kilometers high tracking around the planet. the crust would flex and fracture. The mantle, already semi-liquid at depth, would experience tidal heating on a scale closer to what Enceladus experiences from Saturn's gravity right now. Volcanic activity worldwide would increase. The ground itself would move. That is before you account for the radiation. Saturn's radiation belts, at their current distance, extend outward to roughly 285,000 kilometers from the planet. At Earth's orbital distance from the Sun, Saturn's magnetosphere would engulf everything in the inner solar system out to the Moon and beyond. Earth's own magnetic field would be fighting a permanent geomagnetic storm driven by the interaction with Saturn's vastly more powerful field. The kind of geomagnetic storm that occasionally takes out power grids and disrupts satellites here on Earth. Those are caused by relatively minor disturbances in the solar wind. A permanent, full-contact interaction with a magnetosphere 578 times stronger than ours would be something categorically different. Navigation systems, power infrastructure, communication satellites. None of the systems that modern civilization runs on would function reliably in that environment. And that is still just the electromagnetic disruption. The gravitational influence would reach further than Earth. At Earth's orbital distance, Saturn's gravitational pull on Mars, Venus and Mercury would be strong enough to perturb their orbits meaningfully over geological timescales. The inner solar system's orbital configuration has been more or less stable for billions of years because the planets are spaced far enough apart that their mutual perturbations stay small. Drop a 95 Earth mass planet into the middle of that arrangement and the stability does not hold. Orbital resonances would shift, eccentricities would grow. On timescales of tens of millions of years, the inner solar system's current structure would not survive. Then there is Titan. At its current distance, Titan's surface sits at around minus 179 degrees Celsius, cold enough to keep methane liquid. Move Saturn to Earth's distance from the Sun, and Titan receives roughly 90 times more solar energy than it currently does. The methane lakes would begin to evaporate. The thick orange haze of organic compounds would react faster under the increased ultraviolet exposure. Titan's atmosphere is currently stable, partly because it is so cold. Warm it up significantly, and the chemistry changes in ways that are hard to predict but unlikely to move in a direction that makes the Moon more hospitable. The methane cycle that sculpts its surface would collapse. The rivers and lakes that make Titan look, from orbit, so strangely familiar would drain and disappear. Enceladus is a different problem. Its internal ocean is maintained by tidal heating from Saturn's gravity. Move Saturn closer to the Sun, and the other planets in the solar system exert stronger perturbations on Saturn's orbit and on the orbits of its moons. The orbital resonances that currently keep Enceladus in a slightly eccentric orbit, which is what drives the tidal flexing, would change. The heating rate could increase or decrease depending on exactly how the resonances shifted. An increase would accelerate the geological activity. A decrease might allow the ocean to freeze. Either outcome removes what makes Enceladus interesting. And the rings themselves would respond. Tidal forces at closer range would compete directly with the self-gravity that currently keeps the ring particles organized into their thin disk. The Roche limit, the distance inside which a moon cannot hold itself together against tidal disruption, scales with Saturn's mass and with distance. At Earth's orbital position, the tidal environment around Saturn would be different enough that the ring structure might spread, diffuse, or develop instabilities that the current configuration does not show. The rings that took a moon apart to create them might start to behave differently under the altered tidal geometry. None of this is meant to suggest Saturn is dangerous at its actual distance. It is not. It is a spectacular, strange, deeply complex system sitting 1.4 billion kilometers away, and it will stay there. The point is that every feature we have spent time on, the winds, the internal heat, the radiation, the magnetic field, the tidal effects on its own moons, all of it runs on energy budgets that are already extreme at Saturn's real distance. Proximity would not add new forces, it would just let the ones already operating there reach us. Distance is the only thing standing between the most beautiful planet in the solar system and a genuinely catastrophic neighbour. In 100 million years, Saturn's rings will be gone, not faded, not thinned, gone. Cassini measured the rate directly. Roughly a ton of ring material falls into Saturn's atmosphere every second, dragged down by magnetic field lines and charged by ultraviolet light from the sun. At that rate, the rings have maybe 100 million years left. Some estimates say less. The most iconic structure in the solar system is on a clock, and the clock is already deep into its countdown. What that future Saturn looks like is not a mystery. It looks like Jupiter. Wide bands of cloud, visible jet streams, no rings, no impossible geometric halo catching sunlight from 1 billion kilometers away. Just a gas giant doing what gas giants do. Someone standing on Earth in 300 million years, if anyone is standing on Earth then, would look up and find a planet that barely resembles the one in every photograph from the last 4 centuries of human astronomy. The rings are not a permanent feature of Saturn. They are a phase. We happen to be watching during the phase when they exist. The hexagonal polar storm is a different kind of unknown. We do not know when it formed. We do not know how long it has been maintaining that precise 6-sided geometry. Voyager saw it in 1981. Cassini watched it for 13 years. It was there the entire time, stable, turning slowly, wider than Earth. Whether it has been there for 1,000 years or 1,000,000, nobody can say with confidence. Whether it will still be there when the rings are gone is equally unclear. The conditions that sustain it are tied to jet stream dynamics deep in Saturn's atmosphere, and as the planet slowly cools and its internal heat output gradually drops over billions of years, those dynamics will eventually shift. At some point, the hexagon will lose the conditions it needs and dissolve into something less remarkable. When that happens, no instrument will be there to record it. Titan is running on a different timeline. Right now, Titan's methane lakes sit at the poles, fed by methane rain, cycling through a complete hydrological system that mirrors Earth's water cycle in almost every structural way except the substance involved. That will not last forever. The sun is slowly getting brighter. Over the next few billion years, as solar radiation increases, methane in Titan's atmosphere will be broken apart faster than volcanic and interior processes can replenish it. The lakes will thin, the rain will slow. Eventually, the methane cycle will collapse, and Titan's surface will become a drier, colder, stranger place than it already is. The thick golden haze will thin. The landscape that resembles Earth more than anywhere else in the solar system will lose the feature that makes it remarkable. Enceladus is more fragile still. The geysers at its south pole are driven by tidal heating. Saturn's gravity squeezing and releasing the moon as it moves through a slightly elliptical orbit. That geometry is not fixed. As the moons of Saturn slowly migrate and their gravitational relationships shift, the tidal heating driving Enceladus's interior will change. The ocean beneath the ice may persist for hundreds of millions of years more, or the heat source may weaken faster than current models suggest. The plumes could slow and stop long before anyone from Earth ever manages to sample them directly. Whatever is happening in that ocean right now may not be happening in another 500 million years. The interior of Saturn is the part of this that lasts. The helium rain, that slow, continuous sinking of helium droplets through the liquid hydrogen layers toward the core, will continue for billions of years. Each droplet falling through hundreds of thousands of kilometers of planetary material releases a small amount of gravitational energy as heat, multiplied across the entire interior, continuously over geological time, This process keeps Saturn's core burning and its internal heat output elevated well above what solar heating alone could sustain. This will not stop quickly. The differentiation between hydrogen and helium in Saturn's interior has been running since the planet formed 4.5 billion years ago, and there is enough helium left to keep the process going for billions more. Long after the rings are dust, long after Titan's methane lakes are dry, long after the hexagonal storm has dissolved into something unrecognizable, Saturn's interior will still be generating heat and radiating more energy than it receives from the Sun. Saturn itself as a planet is not going anywhere on any timescale that matters to us. It will cool. It will slowly shrink as its interior contracts under gravity. Its storms will weaken as internal heat decreases over billions of years, but it will remain a gas giant, massive and cold and turning, orbiting the Sun long after every surface feature we have ever observed has changed beyond recognition. What matters is where we are in that timeline right now. The rings may have formed only 100 to 400 million years ago, when a moon wandered too close and Saturn's tidal forces tore it apart. Before that, Saturn had no rings. In another 100 million years, Saturn will have no rings again. The window in which rings exist around this planet is narrow against the backdrop of the solar system's age. The ringed planet we know is a temporary thing, and the fact that we exist during the window when the rings are still there is the kind of coincidence that should feel remarkable. After everything, the winds, the lightning, the hexagonal storm, the radiation belts, the dying rings, the alien moons, it is worth asking what Saturn has actually taught us. The answer is not simple. Saturn has been observed carefully for centuries. Galileo pointed a telescope at it in 1610 and thought he was seeing 3 separate objects. It took another 45 years before Christian Huygens figured out what the rings actually were. For 400 years, the planet has been frustrating people who thought they understood it. That pattern has not stopped. When Cassini arrived at Saturn in July 2004, it carried instruments designed to answer the major open questions about the system. It stayed for 13 years. It returned data that filled thousands of scientific papers. It watched storms form and dissolve. It measured the magnetic field from dozens of angles. It flew through the ring plane. It dropped a probe into Titan's atmosphere. By any measure, it was one of the most successful missions in the history of planetary science. And when it finally dove into Saturn's atmosphere in September 2017, the scientists who built it had a longer list of open questions than when it arrived. That is not a failure. That is what Saturn does. Take the winds. Before Cassini, the leading model for Saturn's atmospheric circulation relied heavily on solar heating driving convection at the cloud tops, similar to how Earth's atmosphere works. The numbers never quite fit, but the framework held. Then researchers started working through Cassini's atmospheric measurements in detail, and the solar heating model broke down completely. Saturn receives roughly 1% of the solar energy per square meter that Earth does. It cannot drive 1,800 km/h winds with that. The energy has to come from inside, from the internal heat that Saturn has been radiating since its formation. The models had to be rebuilt from the ground up. That process is still ongoing. A complete, predictive theory of Saturn's wind structure does not exist yet. The Hexagonal Storm did something similar to atmospheric fluid dynamics. Researchers had known about it since Voyager photographed it in 1981. Laboratory experiments can reproduce hexagonal patterns in rotating fluids under specific conditions. The physics is understood in principle. What the Hexagonal Storm forced scientists to confront was the stability question. A hexagonal vortex maintained with near-perfect geometric precision across decades of observation, through seasonal changes, through storms that disrupted the broader atmosphere. That requires specific conditions to hold constant at extraordinary depth. Models that could explain the shape could not easily explain the persistence. The storm pushed researchers into Saturn's deep atmosphere, into layers they could not directly observe, looking for whatever was anchoring it. That work is still producing new results. Enceladus changed a different kind of conversation entirely. Before Cassini flew through the plumes erupting from its south pole, the search for life in the outer solar system was mostly focused on Europa. Then came the measurements: water vapor, sodium salts, silica particles indicating hydrothermal activity, molecular hydrogen, organic compounds, the chemical signature of water reacting with rock at elevated temperatures, deep beneath the ice in the dark. Hydrothermal vents on Earth's ocean floor host entire ecosystems that run on chemical energy, no sunlight required. Enceladus appeared to have every ingredient those ecosystems need. In one flyby, the boundary of where life might exist in the solar system shifted outward by hundreds of millions of kilometers. The conversation about habitability has not been the same since. Ring rain was a different kind of discovery. The idea that Saturn's rings were feeding material into its upper atmosphere had been proposed theoretically, but direct measurement was another thing. Cassini confirmed it. Roughly a ton of material per second falling from the rings into Saturn's ionosphere, arriving fast enough to disrupt the chemistry, leaving dark bands at specific magnetic latitudes visible from Earth. The rings are not static. They're in active conversation with the planet's magnetic field. Every charged particle that gets pulled down into the atmosphere is traveling along a magnetic field line that connects the ring system to the ionosphere. The magnetic field is not just a background feature, it is the mechanism through which the rings and the planet exchange material. That connection had been suspected but not measured. Cassini measured it, and that measurement changed how researchers model the entire ring magnetosphere system around any gas giant, not just Saturn. Saturn's magnetic field alignment is still unresolved. The standard dynamo theory, the same framework used to explain Earth's magnetic field, Jupiter's, Uranus's, Neptune's, predicts the field axis should be tilted relative to the rotation axis. Earth's is tilted, Jupiter's is tilted, Saturn's is aligned to within a fraction of a degree. The models do not have a clean answer for this. One hypothesis involves a layer of stable, non-convecting fluid above the metallic hydrogen core that acts as a filter, suppressing the tilted components of the magnetic field before they reach the surface. It is a workable idea. It has not been confirmed. Cassini spent years taking magnetic field measurements, specifically trying to get beneath this problem, and the data improved the picture considerably without closing it. The alignment remains one of the genuinely open questions in planetary magnetic field theory. The density paradox sits quietly underneath all of this. Saturn is 95 times the mass of Earth and less dense than water. The structure that produces this combination, a metallic hydrogen interior generating a magnetic field, surrounded by liquid molecular hydrogen, capped by thousands of kilometers of gas atmosphere, is reconstructed almost entirely from physics and inference. We have never been inside it. Cassini's measurements of Saturn's gravitational field gave researchers a way to probe the deep interior indirectly, mapping how mass is distributed through the planet. The results suggested a fuzzy, diffuse core rather than a sharp, rocky center. What exactly constitutes that core? How large it is? How the layers above it are structured? These are questions that current data constrains but does not answer. What Saturn has taught planetary science most fundamentally is that gas giants are not simple objects. The early models treated them as relatively uniform spheres of gas with some atmospheric weather on top. Saturn demolished that picture feature by feature. The atmosphere is not driven by sunlight. The interior is not uniform. The rings are not permanent. The moons are not geologically dead. The magnetic field defies the standard theory. Every assumption that seemed safe turned out to require revision when the data came in. That is a specific kind of lesson, and it applies beyond Saturn. It applies to the gas giants being discovered around other stars. It applies to Jupiter. It applies to the models used to reconstruct the early solar system. Saturn is the best studied gas giant in the solar system, and it is still producing results that require the textbooks to be updated. There is no clean summary of what Saturn is. Not after everything Cassini showed. Not after the hexagonal storm, the plumes of Enceladus, the ring rain, the winds, the lightning, the core burning hotter than the sun's surface. The planet resists summary. The next time you find Saturn in the night sky, that steady yellowish point of light is the most complex thing you are likely to look at tonight, and we still do not fully understand it.